In this example, we will look at a mixing problem where a pond holds 10,000 cubic meters of water and has one stream running into it and one running out. Water from stream A flows in at 500 cubic meters a day, while stream B flows out at 500 cubic meters a day, so the amount of water stays constant in the pond. At time t equals 0, stream A becomes contaminated with road salt at a concentration of 5 kilograms per 1,000 cubic meters. If we assume that the contaminant is evenly mixed throughout the pool, we want to let S be the amount of salt in the pond after t days of pollution and find the function S of t. To do this, we will need to model S of t using a differential equation, because we know the rate at which the contaminant is coming in and the rate at which it's going out. Since we have information about the rate of change, we have information about the derivative. So to build this differential equation, we will want to look at how S of t changes, distinguishing between the rate in and the rate out of that salt contaminant. The salt is coming in from stream A. It's contaminated at a concentration of 5 kilograms per 1,000 cubic meters, and the water is flowing in at a rate of 500 cubic meters per day. On the other hand, the rate at which salt is going out we will also find as the concentration of salt in the water times 500 cubic meters per day, the rate at which the water is streaming out of the pond. The difference here is that we don't know the concentration a priori, so we'll need to do a little work there. Going back to the rate in, since we have a concentration of 5 kilograms per 1,000 cubic meters and a rate of water flow of 500 cubic meters per day, we get that the rate at which salt is coming in is 2,500 kilograms per 1,000 days, which reduces down to 2.5 kilograms per day. We can find the rate out similarly if we know the concentration. The concentration of salt in the water will be the total amount of salt divided by the total amount of water. The total amount of water is given to us with 10,000 cubic meters of water in the pond, and the total amount of salt in the pond is given by the function S of t. So the concentration is S kilograms per 10,000 cubic meters. And this is flowing out at a rate of 500 cubic meters of water per day. Canceling the cubic meter units, we get 500 times S over 10,000 kilograms per day, which reduces down to S over 20 kilograms per day. Combining these, we get that the rate of change of salt, ds dt, which will be given by the rate at which salt is coming in minus the rate at which salt is going out, can be written as 2.5, the rate in, minus S over 20, the rate out. This leaves us with the differential equation ds dt equals 2.5 minus S over 20. Now that we've built this model, we can solve it to find S of t. And to find S of t, we will need to solve this differential equation, ds dt equals 2.5 minus S over 20. To start, we can factor out negative 20 from the right-hand side, leaving ds dt is negative 1 over 20 times negative 50 plus S. And dividing by S minus 50 on both sides so that we can use the substitution rule gives us 1 over S minus 50 times ds dt equals negative 1 over 20. Now that we've written it in this form, as we did in past examples, if we integrate both sides, we get that the integral of 1 over S minus 50 times ds dt is equal to the integral of negative 1 over 20 dt, where the right-hand side can be simply found as negative t over 20 plus a constant of integration c. On the left-hand side, we'll want to use the substitution rule, which says that this integral reduces down to 1 over 50 minus s ds. And here we can do another simple substitution where u equals s minus 50 and have the integral of 1 over u du, which gives us the ln of the absolute value of s minus 50. Let me note that we should have a constant of integration on this side, but we can lump it together with the plus c all the way to the right. Now to solve this for s, we need to exponentiate both sides to undo the natural log on the left-hand side. Exponentiating both sides gives the absolute value of s minus 50 is equal to e to the negative t over 20 plus c, which can be split up as e to the c times e to the negative t over 20. And thus s minus 50 itself will be plus or minus e to the c times e to the negative t over 20. And since c is a constant, e to the c is a constant, and plus or minus e to the c is a constant, so letting k be the constant plus or minus e to the c, we get the solution s of t equals 50 plus k times e to the negative t over 20. And we found the function s of t for the amount of salt in the pond after t days. I want to note that regardless of the value of k, the term k times e to the negative t over 20 will go to 0 as t goes to infinity. So in the long run, the limit as t goes to infinity of s of t will equal 50 for all values of k. We could have come to this conclusion without solving the differential equation, but merely analyzing the equilibrium solutions to the differential equation ds dt equals 2.5 minus s over 20, as we did in our past examples.